Afternoon to everyone. Welcome to the webinar. I am Sera Lazaridou, President of the ICOLD European Club. On behalf of the organizers, the ICOLD European Club and the ICOLD Young Professionals Forum, today we also have Secretary General Alfredo Granados of EURcold and Young Professionals Forum Chair Mateja Klun. We have the pleasure of guiding you through this session. We would like to extend a warm welcome to all participants joining us across Europe and beyond. We also want to welcome the speakers and thank them. We have the pleasure to have with us Mateja Klun from Slovenia. Good afternoon, Mateja. Ioannis Karavokyris from Greece. Good afternoon, Ioannis. Krzysztof Radzicki from Poland. Good afternoon. Teodoro Estrela from Spain, Catalin Popescu from Romania, Rinaldo Murano from Italy, Rémi Tourment from France. They will all share with us their expertise on the strategic role of dams in mitigating flood risk. Thank you all for your contributions today. We are looking forward to your presentations. Before we begin, just a very quick note on the webinar procedures. The session will last approximately 2 hours and a half. Please feel free to use the chat, but please share your questions in the Q&A section function, mentioning to you which speaker you are referring to. We will make sure to address as many as possible questions during the discussion. The webinar is being recorded. The recording will be available online on the YPF YouTube channel the following days. Now, let's get started by providing some information about who we are and by presenting the objectives of the webinar. The webinar is organized by the European Club of ICOLD in association with the ICOLD Young Professionals Forum. The ICOLD European Club consists of 27 ICOLD European national committees. We are currently celebrating 30 years since its establishment back in 1995. The club mainly aims to encourage cooperation and exchange of information among European countries in issues of significance such as dam safety, create European working groups, promote the organization of professional events and trainings opportunities for young professionals, support dams to decision makers and the public. Today, 12 active groups run within the club, aiming to interact and collaborate with ICOLD technical committees, organize events, and focus on emerging issues within Europe, such as floods. Our next main event is the European Club Symposium. This is a very big event for the European Club. It will take place in Poland next September. You may find more information available through our communication channels, which are supported by the Portuguese and Swedish committees. We also promote multiple actions to raise public awareness, including the recently updated manifesto on dams and reservoirs, as well as the annual Dams and Reservoirs Day initiative, which is being held annually in May, and it has the support of many European ICOLD committees and also from public and private organizations and stakeholders in dam engineering. You can also follow the ICOLD Young Professionals Forum on its webpage, LinkedIn page, and YouTube channel. This recording webinar will be uploaded on the YouTube channel. And now we will move over on the webinar objectives. The idea of promoting a webinar on the role of dams during flood events emerged after the severe floods of recent years. Many of these had significant impacts, and from also the realization that we rarely hear about the role of dams play in such situations. This is an overview. The slide presents a timeline of severe floods across Europe since 2000. It does not capture every major flood. It provides a representative overview, highlighting events recorded for their significant impacts, mainly fatalities, and also economic losses and environmental impacts. In today's presentations, we will focus on recent natural flood events. Storm Vaia in Italy back in 2018. Slovenia, the floods in Slovenia in 2023, you can always highlight it with a different color. In Greece, Ioannis and Medicane Daniel back in 2020 and 2023. The floods from Storm Boris in Poland in 2024, and the floods in Valencia in Spain in 2024, and most recently in Romania, there were floods this summer in July in 2025. Now in this graph, we can see that since 2000, fatalities spiked dramatically in certain years. We can see in 2002, there were Central European floods. In 2012 in Russia. In 2021, that was all around Europe, Central, Western, Eastern, Southern and Southeastern Europe, and also Turkey floods. In 2024, of course, we had the floods in Spain. In general, the available data suggest that Central, Western and Southern Europe appear to be most effective in terms of frequency and fatalities, but all these data do not capture the scale of economic losses and the environmental impacts, which are even harder to assess. Another objective of the webinar is to highlight the role of dams in mitigating flood risk within the framework of European directives and national regulations. The EU Floods Directive, as a general framework, recognizes that floods arise not only from rivers, rainfall, or the sea, but also from man-made infrastructures such as dams and reservoirs. However, dams are not recognized only as a potential source of risk. They are acknowledged for the major benefits they provide in flood control. Many reservoirs across Europe are operated to temporarily store flood waters and reduce downstream peaks. The directive requires these operational measures to be documented in flood risk management plans, together with their expected effect on flood reduction. In recent years, member states have also been encouraged to adopt more adaptive approaches, for example, adjusting rule curves or releasing water in advance of extreme rainfall based on forecasts. These actions help to increase available storage and are often coordinated with operators, water agencies, and civil protection authorities. Because the Floods Directive must work in harmony with the Water Framework Directive, any changes in dam operation for flood control must also respect environmental flow requirements and avoid ecological deterioration. Across the EU, this combined approach, assessing failure risk, improving preparedness, and using control operation, shows that dams are viewed both as potential hazards and as vital tools in reducing flood impacts. The overall goal is to ensure coordinated, transparent, and adaptive management of reservoirs within each river basin. Dam safety regulations also acknowledge the important role dams play in flood defense by including operational rules for various flood scenarios and coordination with civil protection agencies through emergency action plans. In some countries, regulations also set specific operational rules that require proactive measures. For example, operators may be obliged to pre-regulate water levels ahead of the rainy season to create storage capacity for incoming floods. I can surely talk about Greece, where large hydropower reservoirs regulate maximum and minimum monthly water levels to provide flood protection while ensuring power generation. But as we move to the presentation, we will see that this is something that's happening all around Europe. The scope of the webinar is to examine the role and performance of dams during severe flood events, looking at how they operate under extreme conditions, also combined with other flood protection systems, especially levees. We will identify and assess their contribution in mitigating downstream impacts, especially in protecting communities and critical infrastructure. We will also review how these functions are reflected in national flood management and resilience planning. Building on real cases, we will discuss proactive practices and real-time decision-making, drawing lessons for operational rules, emergency action plans, and coordination with authorities. And finally, highlight the importance of communicating their role in flood risk management to decision makers, stakeholders, and the wider public. Now, after this general introduction, this slide outlines the structure of the webinar and today's presentations. EURcold Secretary Alfredo Granados will present our speakers. Thank you.
Thank you, Sera. Just a quick reminder before going to the presentations. Please share your questions in the Q&A function, mentioning to which speaker you are referring to, and we kindly request that all participants switch off your cameras during the presentations. And so now we move to the first presentation by Dr. Mateja Klun. Mateja Klun is a research and technical assistant at the University of Ljubljana, specializing in hydraulic structures and reservoirs, condition monitoring of large dams, and structural health monitoring. She's chair of the ICOLD Young Professionals Network, active in ICOLD technical committees, and a member of the UNESCO Chair on Water-Related Disaster Risk Reduction. Dr. Mateja Klun will present the role of dams during the August 2023 floods in Slovenia. Mateja, the floor is yours.
Thank you. Good evening, good afternoon, everybody. Let me just share my screen. Okay, so I'm going to talk about the floods that happened in Slovenia in August 2023. These floods are at the moment recognized as the largest natural disaster that happened to our country since our independence. I'll share some insights on what was happening climatologically and hydrologically, and then focus on the role of dams during these floods. First, so we had a 72 hours rainfall occurring in August 3rd to 6th in 2023. And this was happening on a national scale. So we are used to having severe rainfall happening every year, but not on a national scale. This time the entire country was basically affected. Only 30 municipalities out of 212 were not reporting any damages due to floods or landslides during this event. And in the end, the entire estimated damage is close to 10 billion euros, which is roughly 10% of the Slovenian GDP. And a little bit into the perspective, in 2022, we had the most dry year in the history of Slovenia and the largest fire in our country. And in less than a year, we went from the driest year to the wettest year that we have until we are performing measurements. So there is a quite large contrast, which is something we weren't used in the past to happen to us. So a little bit about the climate and properties of the terrain in Slovenia. So we have 3 climate regions in Slovenia. One is sub-Mediterranean, Alpine, and majority of the countries in the continental climate region. We are having 4 seasons, so we have cold winters with snow. In the past, we had a lot of snow. Now the snow cover is reducing, and we have more or less rain in the winter. Our weather is coming to us from the west, so it's brought by west and southwest winds. And in average, we have about 1,500 millimeters all around the country. But as the weather is forming, we have more rain in the west of the country and less rain in general in the east of the country. The average temperatures in Slovenia are around 10 degrees. Then again, based on the local properties, these values vary quite a lot. So similarly as the weather formation is also our hydrography and terrain. We have a lot of rivers and watercourses, roughly 2 kilometers of river stream per 1 square kilometer of our territory. We have 4 large rivers. Majority of them is flowing to the Black Sea, and one of the large rivers, Socha River, is flowing to the Adriatic Sea. Regarding the terrain, we are located in the region where the Alps, the Pannonian Basin, the Mediterranean, and the Danaric Alps meet. So there is quite a large diversity in the terrain, and also similarly when it comes to weather. When weather front in Slovenia moves for just a few kilometers, basically, when we are talking about warning the nation, an entirely different country can be flooded as just by a little bit of a switch or uncertainty in how the weather is forming. So besides these properties, also our country is very prone to landslides. More than half of the country is identified as an area with high landslide susceptibility. So when it comes to natural events, a lot can happen to us, and a lot has been experienced also in the past. So now in 2023, what was happening in August? Well, basically the weather front that approached us was nothing unusual. Just usually this type of weather happens in Slovenia in autumn and not in the summer. And the year of 2023 was already very wet. So the month of July, before these large floods, had a lot of rain. Some areas had more than 3 times of the average year in the long-term averages. At the same time, the Mediterranean Sea was very warm, so there was a lot of humidity in the air. And the weather front that reached us basically was staying in one position for 3 days, which is also, usually they move a little bit, but now the concentration of the rain basically was forming in one part for the 3 days. We were warned about this, so our weather agency issued a red warning. As you can see here, basically for almost the entire country, the red warning was issued. And again, I need to emphasize this was not the first red warning this year. The month before, we had such red warnings happening almost every week because we had so much rain. Here on this figure is basically the sum of the rainfall that happened during the 3 days in August. And as you can see, the larger amount of the rainfall was happening in the south, in the northwest and north part of the country, and also this is also the area where the springs of some of the major rivers are happening. So basically, what was flowing was directly going into the major river streams, and this reflected, if I show you further on the measurements from the discharges from our river network. Our National Environmental Agency has a distributed network of hydrological stations, and at 122 hydrological stations, extreme flows were measured. Basically 74 rivers across Slovenia were flooding during those 3 days. At 31 stations, the measured flow was a 100-year flood or even larger. And this was also something that is not the usual. The 3 largest rivers, so Sava, Drava, and Mura, they were all flooding simultaneously. This was not something that we have experienced before. Here are some figures from the flooding, the landslide, and the effects that happened during the event. Basically, 17,000 square kilometers of Slovenia were affected. We had over 1,200 larger landslides and a lot smaller ones. Roughly 1,000 households destroyed and 50,000 households affected. At the moment, we are still in the rehabilitation phase. It has been estimated it will take us 5 years, probably in the end even longer, to recover from this disaster. Now, if I go further into the dams, we have in total 43 large dams in Slovenia and additional 28 that have a special operation regimes. Also, we have a large number of smaller dams, mostly located in the Alpine region of Slovenia. The In today's presentation, I will focus on the run-of-the-river schemes because they were the ones that were involved. We have run-of-the-river schemes which are mainly used for the electricity production on three main rivers, on Drava, Sava, and Socha. As I mentioned, run-of-the-river, meaning what flows in also flows out, and they have only limited retention capacity. All of our rivers have torrential character, so we have very high yearly fluctuations of flow, and we have operators that are used to dealing with situations with high flow variabilities. If I now focus on Sava River. So Sava River was, it's basically the largest Slovenian river that has an origin in Slovenia. We have other large rivers, but they are not originating in Slovenia. So what was happening on Sava River? As I mentioned, we were warned by the National Environmental Agency one day before the event that we can expect large flooding. And this means that the operators of the dams need to go into the flood regime. For the dams in the upper reach of the Sava River, there are three dams, Moste Dam, Maučice, and Medvode. They went into lowering the water level in the reservoirs. Moste Dam, which is the most upstream dam, is also the only dam with some retention capacity in Slovenia. It has a weekly reservoir. Moste Dam was lowered for 3.5 meters below the operational level already the evening before, while Maučice and Medvode dams, which are then a little bit downstream run-of-the-river dams, they were lowered for 1.5 and 1 meter. Now, at Moste Dam, the highest peak inflow into the reservoir was at 123 cubic meters per second, and this happened at 4 in the morning on Friday. And they used the available flood capacity in the reservoir to protect the downstream areas because there was still evacuation ongoing. So basically the peak outflow of the reservoir was around 45 cubic meters per second. They had a very large increase of the flow of inflow into the reservoir happening just a few hours before the peak inflow. And similar situation was happening also in the two dams downstream, which lie roughly 40 kilometers downstream, run-of-the-river dams, Medvode and Maučice. They had 100 cubic meters of flow just the evening before, at 8 in the morning on the day of the floods, they had 1,000 cubic meters per second. And the increment in the last 3 hours before the peak flow was 200 cubic meters per second per hour. They had a lot of issues with the large quantity of wood and debris. Basically, they were operating with the spillways. Each spillway has 2 overspilling sections, so they were operating with the spillways in order to flow downstream all the incoming debris and basically stabilizing the flow situation here. They weren't able to keep any water into the reservoir because there is only 1 meter available. So basically what was flowing into the reservoirs was also flowing downstream. Then further down Sava River, Sava River then flows by Ljubljana and then goes into the lower Sava River section where there is a section of 5 run-of-the-river reservoirs. Here the story was a little bit different. So again, we have run-of-the-river reservoirs here, and all the reservoirs were pretty empty in the evening before, so they can lower the reservoirs for 1 meter. And here again, the dams are used for hydropower production, but after we reach the flows that exceed 800 cubic meters per second, it's a flood regime happening here. So besides this project of building these 5 run-of-the-river dams, also the flood retention areas were placed. And this is a relatively new scheme. Basically, it was finished in 2020 with the scheme for the flood protection. And just a few years after the installation, it was already tested. So During these floods, these flood retention areas were activated, and basically we had flows with similar flows in the year 2010 when the last two dams in the chain weren't installed, and they were flooding. Krszko town was flooded and other settlements in this region were flooded, but this time the dams, the flood retention, since with the activation of the flood retention, the settlements were protected. And in this area, roughly 60% of the Slovenian territory, and the territory where at this time we had the rainfall, is inundating. And we had problems, we had floods upstream, but basically this region, due to the dams, was protected from flooding. Here are a few figures from the day of August 4th and 5th. Basically, also here you can see that they had problems with debris as well. And also there was a lot of sediment load because the torrential river carries a lot of sediment during the flood events. But in the end, the system functioned as designed. Besides run-of-the-river schemes, we have also a few dry reservoirs installed in Slovenia. So this is the case of Prigorica Dam in the southeast of the country. This dam was not activated precisely during that event, but the month before, when we had extensive rainfall as well. This is the picture from the month before. Basically, this is the largest dry reservoir in Slovenia. It was activated the entire month before, and it's used to protect the settlements in the karstic region from flooding, and it has worked. So basically it has 12 million cubic meters of volume, and the water that flows through the settlements is redirected to this reservoir, and then it's slowly released downstream. And another case, and I will finish with this case, this is the case in the south of Ljubljana. As I mentioned, we had flooding happening in 2010, and in 2010 also the south part of Ljubljana, of the city of Ljubljana, was flooded. In this time, there were measures to mitigate flooding in the south of the city, including with the building of the dry reservoirs. And in 2023, with similar flow situation, the south part of city of Ljubljana was not flooded because the dry reservoirs did their job. And with that, I'm gonna wrap up my presentation. Thank you for your attention.
Thank you, Mateja. Now, I'm pleased, here we are. I'm pleased to invite our next speaker, Dr. Ioannis Karavokyris. Dr. Karavokyris is a civil engineer with over 30 years of consulting experience in hydraulic projects, specializing in the design and construction of large dams in Greece and abroad, and he has served on expert panels for major projects such as Rogun Dam, and recently coordinated the revised flood risk management plan for Thessaly in Greece. He is managing director of G. Karavokyris and Partners Consulting Engineers. Dr. Karavokyris will present flood defense planning in central Greece within the framework of the EU Flood Directive, with reference to the 2023 floods triggered by the Medicaid Daniel. Ioannis, the floor is yours.
Thank you. I hope I'm sharing, and I hope you can see my presentation.
Yes.
Okay. Well, thank you for the introduction. Yes, we had two large events in central Greece, in Thessaly, in the plain of Thessaly. Thessaly is one of the most productive parts of Greece. It concerns this large plain in the central part. For those who are not familiar, it is bounded by fairly high mountains to the west and some not as high. Well, this is Olympus, which is also high, and some lower mountains, but nevertheless from the east, from the sea. But this setting is very important to what has happened twice in the last 5 years. My presentation I will quickly mention the two Medicane storm events, Ioannis and Daniel, that had similar impact, but of course Daniel was much more impactful, much worse. Some characteristics of the Thessaly plain that are related to flood vulnerability, the development of a flood management plan, and focusing on the role of existing and new dams within this integrated set of flood protection, and some concluding remarks. So if we start with the Medicanes, for those that are not familiar, but I think now we have heard about them quite a lot. We were not familiar with them, only meteorologists were. They're tropical-like cyclones forming in the Med Sea. Well, I mean, they have a similar structure to tropical cyclones. They have an eye, a warm core. They are not as strong as the stronger tropical cyclones, but of course they can be very destructive, and they are in an enclosed sea, so the likelihood of impacting on land is very high compared to a storm in the Atlantic. Now, the formational strength is very strongly correlated to sea surface temperatures. Therefore, we should expect increase in frequency and in severity with climate change. First of all, Ioannis that occurred in September 15th to 21 September 2020. You can see a map of the route. It started just as a low pressure system, just to the west end of the Gulf of Sidra. It moved north into the Ionian Sea, then it intensified. We can see the pressure in the red line below. It fell down to 984, and then it went back, weakening slowly to north of Egypt, to the Mediterranean. But here we can see this in focus window. This is where most of the damage took place. This is a mapping of rainfall depths, and you can see most of the rainfall, highest rainfall occurred in the mountains upstream of the plain of Thessaly, and of course where the low system itself was situated on the Ionian Islands. There was a lot of damage here, but our focus is on the plain of Thessaly today. One can see rainfall. Maximum daily rainfall in Thessaly aerially weighted was 273 millimeters, over the entire event just under 300 millimeters. And there were some stations like Plastira hydropower station, which measured 535 millimeters in one day. So this was a very severe event. And of course it had, as expected, quite severe results, particularly in the western part of the Thessaly plain, because this is where most of the rainfall was concentrated, the high intensity rainfall. On the right picture, we can see the city of Bistrița, another 15 villages. Overall, 5,000 homes were flooded and businesses, and there was extensive damage to cultivations. Now, moving on to Medicane, Daniel, which took place only 3 years later. This concentrated minds, because one can always think that a Medicane like Ioannis was a one-off event, but then we have another one which is worse within 3 years, and not exactly the same, but very similar mechanisms, actually, especially concerning what happened in Thessaly. This event actually, this low system actually did develop in the Ionian Sea to the west of Greece, and then it moved southwards, intensifying, in fact, to Libya, and there in Libya, of course, it caused huge damage because of the failure of 2 dams. Compared to Ioannis, when in Greece, pressure was not as low as with Ioannis. And this is one of the reasons that it didn't cause so much damage where it was located. But as we shall see in the next slide, there were synoptic circumstances, meteorological circumstances that created very high rainfall, again in Thessaly, induced by this system. This is the general synoptic figure for Europe. We had a high system in Central Europe, Central Western Europe, with two lows to the west and to the east. This is not an unusual feature, actually. It's called omega blocking because this looks like an omega. What this does is it induces a persistent northeastern stream towards Greece from the Black Sea, but also, of course, this low induces a circular motion of air, and everything unfortunately met in central Greece. So we had convergence in central Greece. And also what is very important was the abnormal, very high surface temperatures, abnormal, I think 5 degrees above average for the time of year. Surface temperatures in the Aegean that helped the system picking up, the wind picking up a lot of moisture, and also a lot of moisture was picked from the Black Sea. There was considerable flooding also in Bulgaria, on the coastal Bulgaria, and in the European part of Turkey, with isolated deaths. But most of the impact for Europe was in this area that is shown in purple. These are maps of where the different phases, let's call them the Greek phase and the Libyan phase, where the rainfall picked most of moisture. So you can see for the Greek phase, most of moisture was picked up from the Black Sea and from the Aegean. When later the system moved to Libya, moisture was picked from southern Mediterranean, particularly from the Gulf of Sirte. So we can see rainfall depths on 2 different days. You can see first we had rainfall concentrated, the very high depths concentrated to the east, and then next day they moved to the west of Thessaly. We are missing here the very high rainfall that fell on this peninsula, on the mountains of this peninsula. There is a mountain called Pilion, and the city of Volos is here, which was also impacted. But we are concentrating on the plain. But you can see some of the measured rainfall depths. They max in 2 neighboring stations, was 765 and 760 millimeters. This was a record for Greece, and 757. And these are sorted in decreasing numbers. So you can see that we had several stations above 300 in one day. Now, when looking at storm total over the 3 days, above 1,000, of course, is more than 1 year for Greece. So these are huge depths. Not surprisingly, again, we had very big impact. About 10,000 hectares remained underwater almost a year after the event. Overall, the agricultural land that was flooded was much more. There were 16 deaths in Thessaly. I mean, a lot of people had to be evacuated, but about 4,500 people had to be evacuated in an emergency manner by airlifting or by boats. The city of Volos, which I mentioned just now, was damaged a lot under an urban type of flood. Major transport works were affected, and the railway line, for example, was cut for considerable time after that. Total damages were estimated at 2 billion euro, but these are direct damages. I mean, certainly there would have been indirect impact also. Now, we should also mention Libya, because there Daniel led to the breach of 2 dams, and then the flood waves went through the city of Derna, and there were more than 10,000 deaths. This was a huge event for Libya. What I wanted to point out is that besides rainfall, you can see this barrage dam within the plain. This is the main river, Pinios. During the flood, we had a lot of debris coming down, which also affected. This is a 10-meter gate 10-meter width gate. It's not only the flood event itself, the flood water, but also all the debris that affected the capacity of the structures to accommodate the floods. The estimation of the peak floods in this location range because all gauges were destroyed. But there are different estimates. Between 3,500 cumecs is the low estimate, and the 5,000 cumecs is the high estimate. Now, at the same time, it coincided with the second event, the preparation of new flood management plans for the region. So the event happened while the plans were being prepared, and of course this was something that was taken into account subsequently. Just to go quickly through the plans, they involved the preliminary evaluation of flood risk and delineation of zones for more careful study, preparation of updated design storms. We had national design storms before, but there was a new depth frequency duration analysis that took into account the two recent events that I mentioned. Following this, runoff simulation to produce flood hydrographs around the plain, hydraulic simulation in the flood risk zones to produce inundation mapping, evaluation and mapping of risk so that we can eventually combine with hazard maps to have risk maps, preliminary maps, public consultation and a strategic environmental and social impact assessment, and finally the final flood risk management plans, which have now been published. So yes, first of all, the zones of focusing had to be based on past records and on a first fast assessment of risk. And you can see the codification of the different zones for the entire country so that we have a unified system. The depth, duration, frequency analysis was carried out by a team of NTUA, National Technical University of Athens. They applied uniformly the EV3, generalized extreme value distribution, for the whole of the country, and we arrived at grids of parameters for the whole of the country. This is the grid of parameters for Thessaly. As I mentioned, we used HEC HMS. The same was used for the entire country. We had a unified methodology to produce in the surrounding mountainous areas, to produce the hydrographs coming into the flood zone, and then the flood risk zone was modeled by HEC-RAS to produce inundation maps. We also had to map vulnerability, different sensitive infrastructure within the zones, gridded maps. From sensitive infrastructures and populations arrive at grids of vulnerabilities, and this allows us to have risk maps in the end. Type of actions, overall, there were 31 measures eventually after consultation. 9 of them were related to prevention. Prevention mostly had to do with change of land uses, even moving infrastructure and even in some cases villages. Protection, of course, is what we will talk about immediately afterwards, has to do with flood protection in terms of structural measures mostly. Readiness has to do with early warning, development of early warning systems, and evacuation and emergency preparedness plans. And rehabilitation is, of course, obvious. It has to do with repairs of damages. Now, Thessaly has some hydrographic characteristics that influence the type of floods we have and the design of flood protection measures. So there are two plains surrounded by low hills, and then in the periphery we have higher mountains. The two the western and eastern plain are connected by gorges that form a control in the flow. And the same happens with the eastern plain. Its outflow to the Aegean Sea again is controlled by gorges. Now, this means that while we have extensive levee system in the plains, it's not feasible actually to continue an efficient drainage of the whole area into the sea because of the control at the gorges. So it doesn't matter. I mean, for small floods, the levees work well, but for really large events, the levied, the enclosed river networks basically concentrate fast the discharges at the control points, and then you start to have inundation moving upstream. And so the same happens in both plain sections. So the selected strategy really was to try and attenuate mountain catchment hydrographs by dams in the periphery. The rest of the runoff that is generated in the plains, and of course the attenuated flow that will spill over the dams to accommodate in controlled flooding areas, controlled inundation areas, and also to try and manage the large quantities of debris from the mountains, both by the dams and extensive catchment management measures. So this is again some pictures of the gorges and also the area where in the western plain where all flow from all the mountains concentrates and where usually flood starts, flooding inundation starts. But quickly about the catchment management measures, this program is now under detailed design. It's quite an extensive program. It is of course controlled mainly by the forestry authorities, and it involves a number of measures related to reforestation, strategic plantings, standard aerial sediment transport checks like terracing, bands, etc., and small check dams in the ravines and small streams. So this is an extensive approach. And of course, coming to the core of our concern in this presentation, the dams for flood protection. There is already one dam, Smokovo, which is a multi-purpose dam in Thessaly. And when it was designed, flood protection was part of the multi-purpose nature of the dam, was one component. So it was designed with a high freeboard and narrow spillway. It is upstream of the western plains. There was a lot of flooding in the past in the areas downstream of the dam. This dam didn't allow any flooding during Ioannis or Daniel. What happens is in September, when both events happened, these multi-purpose dams, because it's in the end of the irrigation season, they tend to be at least half empty. This was half empty. And in fact, it didn't spill at all. But as we shall see later on, even spills will be much reduced, even with dam at full supply level. The alternative to multi-purpose dam is a dedicated flood attenuation dam, which is expected to be drawn down after its flood event. This photograph is from one in Cyprus. There isn't one in Thessaly at the moment, but it is under consideration for protection of Volos urban center. So, where are dams planned now under the new management plan? The priority dams to be built. Smokovo, I just mentioned, and it already exists. There is Paleoterli, Muzaki, Pili, Neohori, Kaluda, Ioneri, Deleri, and Diokabos. So these are all multi-purpose dams. They had already been considered under a drought management plan, so they can be used for irrigation and water supply. And the idea is to also make sure that they are designed so that they provide flood protection services, flood hydrograph attenuation. Very quickly, how a dam with uncontrolled spillway, free overflow spillway, produces attenuation of a flood. Simply, from FSL, some flood routing storage you have so that enough head is generated to flow over the spillway. Therefore, this flood routing storage, instead of continuing directly, as would be the natural hydrograph of the river, it is attenuated and the volume is eventually released progressively with a smaller peak. This is actually a simulation for Smokovo Dam that already exists. So some examples from the new dams. I don't need to stay too long in this. This is the return period of floods that we tried. This is with dam at full supply level, and this is a dam with more realistically for autumn, which would be at about 50% storage. And you can see, we don't need to look at the actual numbers, but the reductions in peak are very substantial, from 61% for the 50-year flood, 48% for a 1,000-year flood, and the percentage reduction is 100% if the dam is half empty, 100%, so no spilling, and basically no spilling if the dam is half empty. And it is similar for other dams. I think perhaps we shouldn't waste time looking at it, but it's a very similar picture for all of these dams that we have, which I showed the allocations in the map earlier. So really, the most likely event is that for the 50 and 100-year floods, there will be almost no spilling. For this dam, which is a smaller one, for the 1,000-year flood, the reduction is only 35%. But this is also a very substantial reduction. And also an example out of interest, what would happen if we raise the dam and reduce further the spillway, because at the moment 69 meters is the preliminary design of the dam. So we can see that with FSL, looking at FSL, if we reduce further the spillway, the 1,000-year flood from 34% reduction will go to 60% reduction, and for half empty reservoir, from 73% reduction will go to 89% reduction. So one can use this to do an optimization regarding heightening the dam and shortening further the spillway or not. The benefit of a shorter spillway, crest length, is of course a greater reduction of flood peak, and the drawback, of course, is higher maximum reservoir water elevation, which leads to higher dam. So we need the cost-benefit optimization there. But for seismic areas, seismically active areas, should be also taken into account that higher dam freeboard also provides an additional service which allows greater margin of safety against seismic loading. I have here a picture from Sultan Suyu Dam. This picture is after the 2023 earthquakes in Turkey, 7.7 and 7.6 Richter scale. You can see the cracking on the crest, and of course the safety of the dam was ensured because there was availability of freeboard. So one has to consider both when optimizing freeboard versus spillway size. Just a very few words on free overflow, which I mentioned for Thessaly versus gated spillways. Undoubtedly, gated spillways give us a wider choice for flood management policies because they allow us to do a real-time preemptive operation of the spillway. So if we have a stream of meteorological and hydrometric observations, we can preemptively increase available routing volume in the reservoir by opening the gates early. Free overflow spillways are passive structures. Yes, we have to wait for the rise of reservoir level so they can store water that will route and reduce the flood. However, the superiority of gated spillways has to be judged against effective and safe operation, which needs sufficient, institutional capacity and also capacity of plant. So you need enough trained personnel and enough plant for operation of the electromechanical equipment, maintenance, emergency intervention if necessary during an event. So, for example, in the case of Thessaly, where the dams are primarily irrigation and water supply plus flood defense, it is more sustainable to have free overflow spillways. So it is the design of the spillways and freeboard that will give us the flood attenuation and protection component that we require. But if we look at primarily hydropower dams, then gated spillways are probably the option of choice, because the personnel has to be there to tend to be available either at the dam or from where they will be able to quickly tend to the electromechanical infrastructure of the project. Some final design considerations, flood routing in a free overflow dam in particular, but in all dams, is a period where you have large fluctuations of reservoir water elevation. In general, this we avoid in normal operation, so a number of precautions are important. For embankment dams, the upstream shoulder should be designed for these fluctuations in terms of drainage and filtering. So for a dam design for flood routing, these can be higher requirements, more stringent requirements, perhaps, than a dam that will not, only in an emergency event, will experience large fluctuations in reservoir level. Also, for all dam types, the reservoir rim and the reservoir slopes may experience instabilities during rapid fluctuations of levels. So really, part of the design should include good study, survey of slopes around the reservoir, and design of stabilization measures, including provision of better drainage of slopes, if necessary. Just to conclude, in Thessaly, we have found that multi-purpose dams with flood attenuation component are a cost-effective solution for managing downstream flood risks. The fact that they are dual purpose, so they serve to protect against drought and against flood, has made them top priority in terms of budget allocation for us within the overall package of interventions, because for drought management and for better use of water, also irrigation network modernization is a major intervention now planned for this area, but the proposals have been that the dams should be prioritized above all because of their additional flood protection role. And at the moment, these are being implemented under PPP. They have started being implemented under PPP programs. Flood protection dams should be designed as part of a wider plan of flood management interventions, not on their own. I've already mentioned that we cannot avoid other interventions, also creating controlled flooding areas within the plains, and all the rest that we mentioned, such as catchment management upstream. And dedicated flood attenuation dams, not the multi-purpose that we described before, can also be effective, especially in concentrated semi-urban areas where the cost can be justified. And thank you very much.
Thank you, Ioannis. First of all, very interesting presentation. I would like to remind our speakers, and I would like to kindly ask them to keep in time so we can have a good Q&A season after the presentations. And thank you very much, Ioannis. Our next speaker, let me share the screen, please. Next speaker is Dr. Krzysztof Radzicki. Dr. Radzicki is an engineer and researcher with over 20 years of experience in hydrotechnics and geotechnics. His work focuses on the safety and condition assessment of damming structures. He has developed innovative monitoring methods, including leak and erosion detection, and he has led expert assessment across Europe and represents Poland in ICOLD committees on levees and embankment dams. Dr. Radzicki will present observations from September 2024 flood in Poland attributed to storm Boris. Dr. Radzicki, the floor is yours.
Thank you. Good afternoon. Hello from Poland. This presentation was made in cooperation with Boris, Radosław, Andrzej, Agata, and Tadeusz from Poland. Thank you. So, September 2024 flood was created in Poland by GNUA laws, which typically touch us every 15-20 years, since thousands of years probably. So it's typical part of this GNUA law. And this time, well, usually they make precipitation on the south part of the Poland, but it depends. Sometimes stronger or Odra River mountain catchment or Vistula River mountain catchment. We have two main rivers in Poland: Vistula, which cross central part of Poland, and Odra River, which firstly goes along the mountains, and after this border between Poland and Germany. So this time, this was mainly mountain catchment part of Odra River and small part of Vistula River, but it also will be important for this story. And what is important locally, it was exceptional, first time seen precipitation such strong in this part of Poland. And so main precipitation was in this mountain part of Poland after danger of flood was propagated with Odra River. I will present you step by step main critical location and structures, which was the actors of this story. So we have zoom on this region when we had strong precipitation. So here we have Pilchowice, old German masonry dam. We have some old German dams in Poland. So one of them, Pilchowice, was overflowed. Happily, it survived. Small destruction was observed. Now is in renovation. And some conclusion for that is that the old masonry dam survived even when flooded. Verification of the discharge capacity of existing hydrotechnical structure for present catastrophic flows is required with consideration of climate change prediction. If necessary, reconstruct or expand the discharge facilities and adjust the reservoir operation policy is also necessary. After we moved a little here, main rain, let's say, touched Czech Republic. However, flow from this rain goes to the Poland on the Głuchołazy town, and there was a huge flood which also overflowed levees. Also, it will be important for this story later. So we are here, and now we go to the most interesting, let's say, part of this history, to Kłodzko Valley, Mountains Valley. There are 4 new earth dry reservoirs two old German dry reservoirs, one masonry one and second earth dry reservoir. So we can see this region here. Here we have border, Czech-Poland border, and you can see this mountain area. And particularly here also we have very mountain and with forest area. What was also very interesting, you can see here photos from the forest in the mountain. So during rainfall events during this time, forest retention was negligible. Effect on reducing the flood wave. Intensive surface runoff was observed across almost the entire slope. There are 4 new dry reservoirs. You can see them. They were built during last about 10 years, maybe 15 years, and they worked well. Here you can see Rostoki dry reservoir, one of them. So full field, well worked. And some conclusion. So this new constructed dry reservoir operated correctly. However, the small mountain catchments didn't experience the most catastrophic local rainfall that occurred in the Stronie Dam catchment. Some of this new dam significantly reduced local flooding in small towns situated not far downstream from these reservoirs. However, to effectively reduce flood risk in larger cities of the lower Klocko Valley, it's necessary to build a coherent system of a much larger number of reservoirs, verified both hydraulically and economically. So this was the region where these 4 new reservoirs were located. Here we have small old Międzygórze dry reservoir. It's also old German masonry dam. It worked correctly. It wasn't overflowed, just spillway worked. And now we go on the east, here to this mountain small catchment. You can see here is Stronie dry reservoir. Some hundreds meters below it's the Stronie Śląskie town. After 5 kilometers further we have Lądek-Zdrój, Spa old town, and after 30 kilometers down we have larger city Kłodzko, and river, this Biała Lądecka river. So this earth dam, Stronie Śląskie dry reservoir, it was 16 meters high dam with a very small 60 centimeters wall on the top of the embankment. Capacity about 4 million cubic meters, mountain catchment area about 54 square kilometers, constructed according to the German regulation 100 years, more than 100 years ago, about 120 years ago. And this dam was destroyed. There are some very interesting movies about this story, what has happened, very well documented story, so you can watch it on YouTube if you would like. So main rain has happened on 14th September. During one night, most of the reservoirs I spoke about was filled. Also this dam. You can see local people try to build additional small wall with sandbags, and during the night reservoir was fulfilled. In the morning it was still fulfilled, but there was a hope. People observed that there was small reduction of height of the reservoir. However, unfortunately, there was second event of the heavy rain, which came to the catchment, and unfortunately, it created the level of the reservoir higher than the crest. So here you can see this wall of sandbags and some leakages between the sandbags. and some side dams, you can see side dams here, was overflowed. I think the height of the flow was about 10 centimeters, so quite huge flow, and it resisted even 2-3 hours of this situation. Here you can see some overflowing by crest between the sandbags, and unfortunately, after about, I think, 2-3 hours, back erosion has happened, which was prolongated in direction of the crest. After probably this hole created that here leakages, saturated zone, water flow in saturated zone seepage created prolongation of erosion and destruction of crest. And after during about 30 minutes, 30-40 minutes, dam was totally destroyed. Here you can see the effect of the destruction. If you are interested in, there are very nice photogrammetry of the catchment after the disaster made by GeoGlass, which is on internet. You can free use it to look at it. Some small conclusion. So first one, there was unfortunately the pier supports located on the top of the spillway. Not very smart idea. However, it wasn't the main problem of overflow. Just the wave was much more larger than capacity of this reservoir. Also, we can make small conclusion that also we should take care about larger and more robust grades for the bottom outlets to prevent clogging of the bottom outlets. And again, key conclusion. So we need in Poland generally verification of the discharge capacity of existing hydrotechnical structures, dams particularly, for present catastrophic flow. Catastrophic flow is required with consideration of climate change prediction. If necessary, reconstruct or expand the discharge facilities and adjust the reservoir operation policy. So, w stronie dry reservoir, as I told you, can look at it at internet. Some hundreds meters below there is Stronie Śląskie town, destroyed very seriously. Some houses totally destroyed, many houses partially. After 5 kilometers below, we have Lądek-Zdrój town. Here you can see hydrograph. So without this catastrophe, anyway, it could be flooded on about more than 1 meter. But this wave of catastrophe of dam gave additionally about 120 centimeters of depth. Here you can see the hydrograph, and here this peak modelized. This is a peak of the dam collapse, and it has about 1.5 million cubic meters, so the capacity of the dam. Maximum discharge, it was 1,000 cubic meters per second. So here you can see destruction of the town, Lądek-Zdrój. Also there was a large devastation, destruction of the villages and the riverbed between and below these towns. So key conclusion, there was very serious communications failure. During the dam failure, GSM telephone service in the region collapsed and other means of communication proved inadequate. As a result, the warning about the dam failure didn't reach most of the affected communities, and a nationwide review of disaster response communication system is therefore necessary. Also, we can say that the people were used to this dam, that it works. So this failure demonstrates that even smaller dams can pose a catastrophic threat to nearby towns, and we have care about these structures. In the town Kłodzko, approximately 30 kilometers downstream from the dam, the wave generated by its failure didn't substantially raise the flood risk. New dry reservoirs are planned to create flood protection of the region. Only comprehensive system will be efficient. I am proud that with my colleague Bolesław Zatoka, we proposed one of the clever solutions of the two new reservoirs that can protect locally Lądek-Zdrój with smart bypass between these two reservoirs to protect this town. Next, the water from this river goes to cascade of some reservoirs, Topola, Kozielno, Otmuchów, and Nysa. And one of them is interesting because we have destruction of the emergency spillway due to heavy flow. So you can see happily it collapsed very in smart way. Maybe it wasn't smart construction, sheet piles and gabions between, so gabions were taken out by flow, afterwards erosion. However, the sheet piles collapsed each one on another, so in the consequence there wasn't total destruction of the spillway. However, in hydraulic engineering, these details are crucial, and the experience of engineer as well as the transfer of the knowledge between generations are indispensable. And we have the problem with that in Poland. We don't have enough hydraulic engineers. We don't have enough transfer of knowledge between generations. After we have Nysa reservoir in the end of this cascade, unfortunately, there was a flood in the city due to two reasons. First one, I told you about Głuchołazy town flood here. So flood overflowed Livis and goes to Nysa town. However, also there is a problem also with the dam, which gives not. They thought, official stories like that, they thought they pass 100 cubic meters per second, but in reality, probably it was something like 1,600 cubic meters per second. It means there was a mistake. And of course, now explication of these mistakes, this is a serious, let's say, problem and investigation. However, and we cannot speak a lot about the reasons. However, it's important in hydraulic engineering to take care about the details of exploitation of reservoirs. Some information sometimes missed between person, transfer of information could be crucial in consequences. For example, like flood in the town. After we have large Racibórz Dolny earth dam, large dry reservoir here from the entrance from Czech. So here was also quite strong precipitation, which comes to Poland. There is a large reservoir, 118.5 cubic meters, fulfilled almost in one day. It works very well, twice reduce the wave, and also make delay of this wave on Odra River. So wave from Nysa Kłodzka can pass before the second wave from Odra. So it was very important role of this Racibórz reservoir in flood protection on Odra River. However, there was some serious problems with backward erosion processes. They were happily protected. However, this dam was constructed after 2010. In 2010, I proposed very modern system of linear sensors to detect all leakages automatically. Unfortunately, in this time, decision makers not approve it. First system like that was created in Poland in 2014. Condition of dams in Poland, so many of them are in inadequate state. So as conclusion, given the large number of damming structures in Poland, many of which are in inadequate technical condition, a key solution is the use of modern testing and monitoring method to optimize repairs and minimize the risk of failure. And 3 last slides. I told you also here Vistula river catchment. Part of this precipitation in September also touched this catchment. And there is large Goczałkowice earth dam, 160 cubic meters of capacity. Happily, it has low, during drought, it has low water level, and it was capable to catch all flood, all wave. Happily, because just below this dam, there is small mountain, Iłownica River, where flood has estimated return period about 1 times every 1,000 years, so very huge. So this small river fulfilled main Wisła River, and happily Goczałkowice zbiornik catched all wave. So the total losses caused by September 2024 flood in Poland exceed 13 billion, about 3 billion of euros. And final conclusion, large flood control reservoirs such as Racibórz Dolny or Goczałkowice Dam are crucial for flood protection of vast areas of the Poland country, and they fulfilled this role during September 2024 flood. In mountain catchments, only system of smaller reservoirs can provide an effective reduction of flood risk. Dams in Poland must have the discharge capacity of the hydraulic structures verified for catastrophic flow resulting from increasing climate change. If this capacity is insufficient, spillway structures should be expanded or reconstructed and or reservoir operational instruction revised. For this reason, and considering the unsatisfactory technical condition of many damming structures in Poland, it was largely a matter of luck that no other dam disaster occurred beside the failure of the Stronie Dam. Communication and warning systems for natural technical disasters, including dam failures, must be verified and, if necessary, improved. The development and implementation of modern system method and methodologies for testing, monitoring, forecasting precipitation, rainfall runoff transformation, flows, and dam performance are key to minimizing flood risk and optimizing the repair and modernization of damming structures. Thank you for your attention.
Thank you very much, Krzysztof. Very interesting observations and conclusions. It is very nice also to have the possibility to find some more information by GeoGlass, for example. So thank you very much for your presentation. And now I'm pleased to present our next speaker, Dr. Teodoro Estrela. Dr. Estrela is a senior civil engineer with extensive experience in water management, planning, and hydrology. He's a civil servant of the General State Administration, where he has served as Director General of Water of the Ministry for the Ecological Transition and the Demographic Challenge. He currently works at the Júcar River Basin Authority as Deputy Director and Head of the Hydrological Planning Office. He has also held leadership roles in international basin networks. His work in water administration has been compatible with academic and research fields as an associate professor at the Polytechnic University of Valencia. Dr. Estrela will focus on the October 2024 floods in Valencia and on flood management aspects, including the role of dams. Teodoro, the floor is yours.
Thank you, Alfredo. I thank you for your invitation and good afternoon, everybody. I will start my presentation with an overview of the flood management in Spain, and then I will give some views about the October 2024 flood in Valencia, Spain. Can you see the presentation? No? Can you hear me?
Yes.
Can you see the presentation?
Yes, we are sharing the presentation, but you can share it if you want.
You can share the presentation. First, I was saying that I will give an overview of the water management in Spain, flood water management in Spain, and then I will describe the case of the 2024 flood in Valencia. And flooding in Spain, the extreme rainfall is the main cause of flooding in our country. And one characteristic of our floods, there is a great disproportion between ordinary and extraordinary flows, as later we will see, especially in the Mediterranean basins. We have intense rainfalls over a short period, and that means short time to react. And this is a very important question. And furthermore, the climate change may worsen the situation in the future. In Spain, in the 80s of the last century, a turning point in the flood management took place, mainly as a consequence of the Thos dam break. And after this event, start the development of the automatic hydrological information system in the year 1983. And today we have a system that covers all the country. We have information on real time about the main hydrometeorological and hydraulic variables. Related to reservoirs, we are receiving information in real time about more than 300 reservoirs that are managed by the state administration. Later, also more than 14 years ago, no? The water law and the hydraulic public domain regulation established riverbed and flooding zoning in Spain. That really has been very important to avoid damage in the flood plain. No? In the year 2008, a new zone was added, what we call the preferential flow zones, and then important land use restrictions were established in the year 2016. And now I can say that new changes are preparing in our regulation after the October 2024 flood in Valencia. consequences of all these advances in the year 2008 was introduced in the regulation a national mapping system of flood-prone areas. And then this system was created in the year 2015, and it allows to the citizens to consult hazard maps, hazard and flood risk maps in all the Spanish territory. You can see in the future an example of the hazard map corresponding to the Turia River in Valencia, corresponding in this case for the 100-year return period flood. This has been an area that has been affected by the 2024 flood. And also we all the EU countries follow the EU flood directive, and we are developing now the new flood risk management plan. As you know, this plan focuses on prevention, protection, and preparedness, and establish program of measures to reduce the risk based on risk maps. And the last flood risk management plan in Spain will approve in 2023, and we are working in the new plans. But the consequences of the flood of the last year, of the October 2024, has obliged to prepare a previous flood risk management plan in order to be approved and to be able to develop some actions in the next years, without waiting to the year 2027. That is scheduled to approve this management plan according to the directive. Now I will go into the flood corresponding to this isolated depression at high level of 29th of October of 2024, and I can say that we had very heavy and intense rainfall. You can see in the future the map of rainfall on 29th of October for the whole of the country in Spain, and in the right side of the slide, the rainfall in the Pollo ravine that was in the basin more affected, as I will mention later. No, and I should like to highlight that we had very, very extraordinary precipitation intensities. We measured more than 700 millimeters in a few hours in an important area of the Valencia province. A large area was affected in Valencia. You can see in the future the affected area, all the municipalities that were affected. You can see also Valencia. This painted in rose color in the future. You can see the flood area that mainly was due to cause of water, the Magro River and the Pollo ravine. Also in some part of the Júcar basin, in the last part of the basin. But the main basins that produced this flood was the Magro River and Pollo River. With not very great surface, the Magro River has a surface of 1,500 square kilometers, and the Pollo ravine of 450 square kilometers. And I should like to highlight that in case of the Magro River, we have a reservoir, the Forata reservoir, and in the Pollo ravine there is not a reservoir, according to the experts, that was not feasible to construct, to build dams in this basin due to the characteristics of the upper basin, and it's a basin without reservoirs. No, in the case of Magro River, there is one, as I have mentioned. This area has a very high urban and industrial occupation. All the territory is occupied by people, by railways, by roads, by highways, by industrial areas. It's living in this area affected by the flood, the area that is painted in blue color. Is living approximately 400,000 inhabitants. No? And what is really very important, there were 229 fatalities in this area. It was tremendous. And 18,000 millions of euro of economic impact. 18 billions of economic impact in this area. And I have mentioned in the Magro River, we have a reservoir. It's the Forata Dam. And the basin draining by receiving the reservoir is approximately 1,000 square kilometers. I have mentioned previously that all the basin is 1,500. 2/3 of the basin are controlled by the reservoir. The volume capacity is about 37 millions of cubic meters, and the spillway capacity for 930 cubic meters per second. And you can say in the future the importance of this reservoir during the development of flood. This is the line in blue is the inflow to the reservoir. And the line in Greece, the outflow of the reservoir, important volume was storage in the reservoir. It was mainly not empty, but almost empty. And then it was an important effect of attenuation of flows downstream of the reservoir. In the Pollo ravine, I have mentioned that it's difficult to construct, to build reservoirs in the upper basin. The basin is not very large, 450 square kilometers. And I should like to mention the mass inflow discharge was greater than 4,000 cubic meters per second. I want to highlight 400 kilometers has produced 4,000 cubic meters per second in the point of the peak of the hydrodraft. These are the different hydrographs in the main course of the ravine and in the main tributaries of the main course of the ravine. We have developed during this last month different hydraulic, first hydrological models, hydraulic models. We had some models as a consequence of the development of the flood risk management plans, but we have had to adapt the models. In some rivers, as for instance the Magro River, the section has been increased 30% of a consequence of the floods. No, the digital terrain model has changed as a consequence of the sediment in the produced. No, and we have to adapt the models. and simulate first in order to know to have a good knowledge of the flood, and then in order to take different measures for the future. No? This the evolution of the flood in different hours. As you can see, the response very fast. No, in the Pollo Ravine, the response time is 2-3 hours. And it's difficult to take measures in 2-3 hours. No? As I have mentioned, the flows estimated in the Pollo Ravine are greater than 4,000 cubic meters per second, much higher than 500 years return period that were studied and were defined as 1,500 cubic meters per second. And we are talking about a very extraordinary flood. And we have to rethink the flood risk management plan carried out to date in this basin and another Mediterranean basin with very short hydrological response time and consequence very short time to react for protecting people and flooded areas. No? The experience of the DANA makes it desirable first to consider regulatory change in flood-prone zones management. We are working on that, and in the few weeks, surely we have a modification, important modification of the regulation. We have to improve the early warning system. We have good automatic hydrologic information system and models, but we have to improve on it, especially in basins of with very short response time. No? It's important. What are we able to do with this kind of system in this kind of basins? No? Also, it's very important to promote the adaptation of self-protection measures, and then the need of integrated solutions. No, we are working in an important program for adaptation to flood risk in all the flooded affected areas, helping the development with for the citizens and for the industrial areas, etc. Here we have some example of watertight doors, barriers, elevation of accesses, for instance, in this case, an industrial area, etc. A lot of industries have also been affected, and they don't know if to continue in this area, what to do according all that has happened in this flood. No? And I mentioned that it was very important to integrate different solutions. No? Now, in this area, we are working in forestry intervention and the headquarters of the watersheds in order to reduce peak flows and sediments with small dams. Now we have approximately 30 small dams that receive flows and sediments. We have first to empty of sediment these dams and then to construct new small dams in these upper basins. Then, and this one of the more important actions to be carried out to develop flood control areas in order to reduce peak flows, especially in the Pollo Ravine, where it's difficult to construct dams. In the case of the Magro River, it can be constructed any other dam complementary to the Forata dam, but it's difficult in the Pollo Ravine basin. For instance, we are working in control storage areas to reduce the peak flows. Also, in some cases, we are thinking on green ways for diverting water flows, following the way of the waters, following the whole areas of and the water is overflowing in both margins, life and left. In order to increase the basin's drainage capacity, and then to improve some channelings that there are in all this area, adapting and improving the capacity of the channels in order to reduce overflows, especially into urban areas. For instance, all the control store areas that we are working are mainly rural areas, and we are studying different solutions in this area. But it's important because in some cases we need to excavate excavations in the terrain. In other cases, we have to increase some roads, and we are studying the best working of these areas in order to reduce flow discharge. And it's very, very fast what I wanted to tell you. Thank you for your attention.
Thank you very much, Teodoro, for this insightful presentation. And now we are moving to our next speaker. Just let me share the presentation, share the screen, please.
Can you see?
Yes, okay. Just let me. Yes,
thank you.
I cannot share the screen right now. I'm presenting Dr. Catalin Popescu. Dr. Popescu, yes, could you hear me?
I'm Rinaldo Murano.
But the next speaker is Dr. Catalin. No, is Rinaldo Murano. Sorry.
Okay.
Rinaldo Murano is a senior civil engineer and head of the division for hydraulics and applied geology at Italy's Ministry of Infrastructure and Transport. He has over 30 years of experience in dam safety, hydrological and seismic assessment, and technical oversight of new and existing dam projects. He also leads EURcold Observatory on dam maintenance and rehabilitation. Mr. Murano's presentation will address the hydraulic safety of large Italian dams and the application of flood control plans, illustrated through regulatory frameworks, climate change impacts, and recent case studies. It will also include observations from the October 2018 Bahia storm, which severely affected the Dolomites and northeastern Italy. Mr. Murano, the floor is yours. Thank you.
Thank you. Good afternoon, everybody, and thank you for the nice introduction. I would like to begin my presentation with a very brief introduction to explain some simple definitions indicated in the Italian technical regulations. Then I would like to talk about two topics concerning the hydraulic safety of territories. The first topic concerns the flood control plans, which allow the use of large dams for hydraulic protection of downstream territories. The second topic concerns the hydraulic safety of large dams themselves. So for each of these topics, I'm going to present a short framework of current Italian legislation and then some case studies. First of all, according to the Italian legislation, a dam is defined as a large dam if its height is greater than 15 meters or the volume of the lake is greater than 1 million of cubic meters. According to these criteria, in Italy, we have counted 522 large dams, classified as you can see in this graph, and on the right you can see the same graph in percentage terms. This picture represents the territorial distribution of large dams in Italy. As you can see, the dams are mainly concentrated along the...
Excuse me, Mr. Murano, you haven't shared the screen. Could you please share the screen?
I shared it. I try again. Can you see it?
Yes. Perfect.
Okay.
Thank you.
I can begin if you want. I can restart. I was saying, first of all, according to Italian legislation, a dam is defined as a large dam if its height is greater than 15 meters or the volume of the lake is greater than 1 million of cubic meters. According to these criteria, in Italy, we have counted the 522 large dams, as you can see in these two graphs. This picture represents the territorial distribution of large dams in Italy. As you can see, the dams are mainly concentrated along the Alpine Arc and along the Apennine Ridge, as well as on the mountains of Sicily and Sardinia. But after this brief introduction, now let's begin speaking about the first topic, the flood control plans, the so-called lamination plans. In Italy, we use this term. I would like to share with you this first slide that, although not entirely exhaustive, provides an overview of the laws and the directives which have followed one another, starting from the second half of the 80s. The main document is highlighted in the blue panel that indicates the directive of the President of the Council of Ministers of 2004. It introduces, for the first time in Italy, the discipline of the lamination plan, a flood control plan that has to be drawn up to use the reservoirs in order to protect territories downstream of the dams from flood events. But the matter of emergency management and the more general aspects connected to hydraulic risk downstream of dams have been revised and included in the 2014 directives, which we can see in the green and in the orange panels. Actually, they update and integrate the previous procedures. As we can see from the arrows in the slide, there is a strong interaction between these documents. In particular, the PDL, the lamination plan, the flood control plan, modifies and integrates the civil protection document, DPC, which in turn, together with the studies of the propagation of artificial floods, constitutes the reference framework for drafting the Dam Emergency Plan, PED. What is essential is that the documents for each dam have to be consistent, even if drawn up and approved by different administrations. And now let's focus our attention on the 2004 directive. It was the first, I told before, to systematically identify the presence of reservoirs on the territory, intended for the regulation of flow as a possible resource for mitigation of hydraulic risk in downstream areas. Furthermore, the directive of 2004 established for the first time that through specific studies, those reservoirs that could effectively be useful for flood control and therefore for reducing hydraulic risk downstream of reservoirs themselves must be identified. In order to make the volumes useful for flood lamination well in advance, two different procedures can be used, defined as static program and dynamic program, from which the distinction between static lamination plans and dynamic lamination plans. The static lamination plan provides for the continuous keeping of a reservoir level lower than the authorized operating level during periods of the year considered critical for the occurrence of flood events. On the other hand, the dynamic lamination plan operates in real time, requiring the execution of preventive and ongoing discharge maneuvers to be activated based on quantitative forecast of rainfall in the upstream basin and on the resulting expected flow into the reservoir, as well as on the state of the reservoir and the territorially sustainable flow rate downstream of it. The 2004 directive introduced flood control plans. However, especially before the issuing of this directive, in many cases, some large dams in Italy have been subject to operating limitations aimed at the same flood control with other regulatory provisions different from the lamination plan, with the same purpose of mitigating the hydraulic risk of downstream territories. The table shows some examples of dams subjected to reservoir limitation, classified according to the reason of the limitation. Overall, today we have only 37 large dams subjected to reservoir limitations for flood control, and in my opinion, we should increase that number. Now, a case study let's see what happened in 2018 with the Vaia storm. The Vaia storm was an extreme weather event that affected the northeastern part of Italy, particularly the mountainous area of Dolomites and the Venetian Prealps. The event started from a disturbance of Atlantic origin, which, within the context of a severe wave of bad weather over Italy, also impacting nearby regions of Switzerland, Austria, and Slovenia, brought to the area extremely strong winds and persistent rainfall. The very strong wind, blowing between 100 and 200 kilometers per hour for several hours, caused the fall of millions of trees, thus constituting a huge natural disaster. Here we can see, for example, what happened to Comelico Dam, with thousands of trees close to the dam swept into the reservoir. The flood, how I said, affected several municipalities in Veneto, Trentino Alto Adige, and Friuli Venezia Giulia regions. The heavy and abundant rainfall caused the Piave and Brenta rivers to overflow, while the Adige Garda Lake tunnel was open to prevent the overflow of the Adige River too. In the mountain areas, several streams burst their banks and many landslides occurred. Now I would like to show you how a dam was able to mitigate the impact of the flood. I'm talking about the Ravedis Dam on the Cellina River, realized with the primary function of flood control and the additional function of regulating flow for irrigation and for hydroelectric power production. It has 22 million of cubic meters allowable to manage to face floods, 22 millions of cubic meters. As you can see in the picture on the left, the Ravedis Dam is situated in the northeastern part of Italy. And since 2014, this reservoir has a static lamination plan approved by a specific resolution of the Friuli Venezia Giulia administration. This is a picture of the dam where we can see the two large surface spillways situated on both sides of the dam. Before the construction of the Ravedis Dam, the city of Pordenone was often flooded, as we can see in this picture of the 2002. This caused many problems, of course, to the rural area of the city. As we said, in October 2018, Storm Vaia hit this large part of northern Italy, including Friuli Venezia Giulia, and the Cellina flood was particularly intense upstream of the dam. In this case, the Ravedis Dam has helped to prevent many towns and the city of Pordenone from a possible new flood. We can see it better in this graph. This graph, in fact, shows the lamination effect produced by the Ravedis Dam on flood wave of the Cellina stream entering the reservoir during the flood event. As we said, the Cellina flood was particularly intense. It can be noted that the incoming wave had two peaks. The first one equal to 660 cubic meters per second. And the second one, more significant, equal to 1,477 cubic meters per second. The outgoing wave, in red, was strongly laminated by the Ravedis reservoir. The outgoing peak was in fact equal to 862 cubic meters per second, with a reduction of about the 42% of the peak. So, as we said, the Ravedis Dam has therefore helped, has really helped to prevent many towns and the city of Pordenone from a possible new flood. From here, the importance of this kind of works to protect cities and towns and countries downstream of dams. Now let's focus on the second topic, hydraulic safety for large dams. We have seen that the use of reservoirs created by large dams can be useful to protect downstream territories, but it can really be useful only if the dams have a structural and functional safety, and if their discharge system is correctly designed and realized to handle floods. So, to better understand the problem, I would like to shortly tell something about the historical evolution of the construction of large dams and of the development of technical regulation in Italy. As we can see in this graph, the first 10 large dams were built in 19th century. And other 31 large dams were built in the first 20 years of the 20th century. As we can notice, overall we have the first 41 large dams built in the absence of technical regulations, and the remaining 481 large dams built on the basis of technical rules that have been updated over the years. But what is important is that the average age of large Italian dams is about 70 years. And it means that about the 90% of existing large dams were hydraulically designed and built with empirical criteria, often derived from qualitative correlations, from professional experience of the designer, without the systematic support of modern probabilistic analysis, of modern probabilistic models. Therefore, taking into account the average age of large Italian dams, and on the basis of the above-mentioned considerations, aiming to assess the safety condition of existing large dams, in 2004, the Italian legislator has also decided that the Italian Dam National Authority had to provide for a complete reassessment of the hydraulic safety of all large dams. If we come back just for a moment to the previous graph, we can see when it happened. As I said before, this regulatory provision has prompted a comprehensive reassessment of the hydraulic safety of almost all large dams in Italy. But this necessity has become even more evident considering the observable impact of climate change affecting the entire national territory, and we could say also the whole world. So, to take also these climate factors into account, the last Italian dam regulation of 2024, for the first time prescribes that in case of a flood event characterized by an inflow rate greater than the maximum return period of 200 years, or the use of at least 2/3 of the capacity of the surface spillway, in at least one of these two cases, the dam manager shall submit to the General Directorate for Dams an update re-evaluation of the hydraulic safety of the dam, and of course of the adequacy of the discharge systems too. Coming back again to the previous graph, this is the moment it happened. Therefore, starting from 2004, an intense activity of re-evaluation of hydraulic safety of large dams is being carried out. The current situation is summarized in this table. Now, I would like to show some case studies of hydraulic safety improvement works carried out on large dams. Let's begin with Campo Tartano Dam. The design flow rate was 194 cubic meters per second. The re-evaluation led to 246 cubic meters per second, with an increase of the 27% of the original. The consequent works were performed in 2007-2009, and they consisted in a surface enhancement and in the construction of a new bottom outlet. The Rimasco Dam, the design flow rate was not determined, it is an old dam, but the discharge original capacity was about 500 cubic meters per second. The re-evaluation led to 770 cubic meters per second, with an increase of the 53% of the original. The consequent works were performed in 2014-2016 and consisted in the construction of a new bottom outlet. Cazul Dam in the northeastern part of Italy. The design flow rate was 440 cubic meters per second. The re-evaluation led to 700 cubic meters per second, with an increase of 59%. The consequent works performed in 2019-2021 consisted in a crowning elevation and in a surface spillway widening. The last one, Barcis Dam. For this dam, the design flow rate was 1,400 cubic meters per second. The re-evaluation led to 2,500 cubic meters per second, with an increase of the 79%, a great increase. The consequent works have begun in 2024 and they are still in progress. They consist in the construction of a new surface spillway that you can see in this picture on the left. And it is situated quite far from the dam. Here is the dam, here is the new discharge, the new surface spillway. Here I represent some design drawings of the new spillway. The intake structure will be controlled by 3 flap gates, 10 meters high, 10 meters wide and 4 meters high. The gallery, with a diameter of 9 meters, will be about 300 meters long. And at the end of the gallery, we can see there will be a concrete restitution structure shaped like a ski jump, which returns water to the riverbed about 400 meters downstream of the dam. So, at the end of this work, these following conclusions can be drawn. First of all, the presence of a dam can have an important function for the hydraulic protection of downstream territories, and this kind of solution should be used more. Where possible, it is considered advisable to prepare a lamination plan, a lamination flood control that is more oriented towards dynamic rather than static flood control, capable of guaranteeing equal safety standards in the downstream territories, but determining less impact on the availability of the resource. It is also important to take climate change into account. And finally, the dam itself must ensure intrinsic hydraulic safety, thereby enhancing resilience against extreme hydrological events. Well, I finished my presentation. I hope it was of interest of you, and I desire to thank you for your attention and good continuation of the webinar.
Thank you very much, Rinaldo. And now we move, and also for keeping in time, and now we move to Dr. Catalin Popescu, our next speaker. And Dr. Popescu is Technical Director at Aqua Project and a lecturer at the Technical University of Civil Engineering, Bucharest. He has extensive experience in dam safety and infrastructure design. He has led major pump storage projects and master plans in Romania and internationally. He chairs the Romanian Committee on Large Dams and represents Romania in ICOLD technical committees. This talk examines the late July 2025 flash floods in Romania, highlighting human impacts, rapid hydrogeomorphic damage, and the operational challenges faced by dams under extraordinary floods and debris conditions. Dr. Popescu, the floor is yours.
Thank you so much. Please let me know if the presentation is shown.
Yes. Now, perfect.
Okay, thanks so much. So I will begin by telling you where we are actually now and where the flood events happened. They happened in the north of the country, exactly just upstream of one of the oldest and largest reservoirs that we have, situated behind one of the largest dams in Romania, is Muntelui. Just at the end of July, there was some commotion about the probabilistics on the maximum hydrological events that would happen, but nothing could have prepared exactly what happened there. So in this July, we had a very rapid rise in river levels, and the hydrological effects were constant for about 3 days. There were a lot of damages and a lot of human life losses due to the fact that nobody was actually very prepared to actually intervene. It was some works for the river training had been carried out during the past 20 years, but unfortunately they were carried out for some flows without taking into account the climate changes. So these ones were carried out, the protection works were carried out for a maximal exceedance probability of about 1 in 5. What happened actually, the precipitations convected. We had, according to locals, because there were no actual stations, weather stations there, more than 200 millimeters per square meter in about 12 hours, whereas in the whole basin there were about 35 to 90 liters per cubic meter per square meter in the basin. And what happened exactly in this in one of the tributaries was that a rapid concentration and violent floods happened with a lot of massive transports of wood, debris, vehicles, and so on. These flash floods happened, and they happened in a very, very short amount of time. And what took us by surprise is the magnitude of the effects, firstly, and secondly was the fact that it lasted for about 3 days, and the peak of the flood was actually very extreme. As you can see, these are images from the 3 days of the floods, and the flood outcome was about more than 100 million euros of damage. As you can see here are the heights of the water level, and a lot of houses were destroyed. It's quite normal. Where we had the reconstruction of the peak discharges for this tributary, we had about 280 cubic meters per second on a tributary, and on the main river we had about 500 cubic meters per second. This all happens just upstream of the large reservoir. As you can see here, we had 3 gauging stations. These gauging stations were situated all upstream of the reservoir. This reservoir has about 1,200 million cubic meters, and on average, we had these hydrographs happening here. So what you can see is that we had a very, very high discharge of about 500 cubic meters just in the back of the reservoir. And the reservoir, of course, due to the fact that it has a lot of capacity, it held up until the end of the flood with no problems. Just a few words about the basin. So where everything happened, it happened just upstream of the reservoir, and then all the basin is regulated by about 11 dams downstream and 1 large dam, 1 regulatory head of cascade. And as you can imagine, nothing happened after the control of the reservoir. The dam itself it has almost 75 years of existence. It has been built during the 1950s for a period of about 12 years. It's of class 1 importance and category 1, category A. It's multi-purpose. It has a capacity of 435 gigawatts hour of energy, and it stores about 1.2 million cubic meters. It's a gravity concrete dam, as it was the custom in that period for building dams all over Europe and mostly in Romania. It stood the test of time very well, and it has 4 bottom outlets and 4 spillways controlled by gates. there are no problems in whatever happens here. The active storage is about 872 million cubic meters, and the reservoir houses just under 100 million cubic meters of flood attenuation. As you can see, it's being built in for 0.01 probability of exceedance, which is 2.4 thousand cubic meters per second, and with a flood of 493 million cubic meters. The outcome, of course, everything flowed in the back of the reservoir. Everybody had to clean up for about 1.5 months to actually get rid of the wood debris and everything that happened here. And this was the outcome of these 5 days. As casualties, there were 3 lives lost at least, and more than 300 people were displaced. A lot of them were evacuated. There were a lot of homes destroyed, more than 200, and the actual material losses gained up to about 90 million euros region-wide. The main hydrological drivers were the convective rain, and the reconstructive peaks yielded up to 500 cubic meters per second. Just before I would wrap up, one of the outcomes of this extreme event could have been avoided just by having one non-permanent reservoir just upstream of the town that was flooded. It would have costed just about 12 million euros, and it would have spared everything that happened there, so with minimal losses. So just by doing a small calculation, just about 8 to 9 times investment return on a dam that is about 35 meters high and just about 200 meters in spread. So thank you for your attention, and if you have questions, I can answer in the Q&A.
Thank you very much, Catalin. And now our final speaker is Remy Tourmand. Remy is a senior researcher at INRAE, a French public applied research institute specializing in dam and levee safety for over 30 years. He coordinated the International Levee Handbook, leads research and expertise on levees in France, and serves as vice president of the French Committee on Large Dams, as well as chair of EURcold's European Working Group and ICOLD Technical Committee on Levees. Remy Tourmand will focus on the role of levees in complementing dams for effective flood protection. Remy, the floor is yours.
Thank you, Alfredo. Can you see my presentation?
Yes.
Okay, so we are quite a little late, so I will not read all the text in my presentation, and you will be given the possibility to download it. So I will concentrate on the key issues that I want to share with you. This presentation at the end of this seminar is about levees, not dams, which is the main topic of today's webinar, and hopefully we will have more webinars in the future to talk about levees. So you have on the screen the outline of the presentation. First of all, a point of vocabulary. What are levees? Levees are also known under different names, even in English-speaking countries. Dikes, flood defense embankments are more local names like burn stop banks, while levees are raised predominantly of structures to provide protection against fluvial and coastal flood events along coast, rivers, and artificial waterways, so not only on rivers. What's the difference between levees and dams? There are many similarities because they are all hydraulic retaining structures, but also many differences. Levees are usually much longer than dams and lower. The water loading on flood protection levees is occasional, and not permanent. Levees are often old structures, particularly in Europe, built by the local population without proper engineering. Over the time, as you can see on the picture, levees are suffered multiple breaches during major flood events. They have also been repaired, raised after floods, and this leads to a general heterogeneity in materials in all dimensions, in the cross section, as you can see on the picture, but also in the third dimension or along the length, because they were built with local material, very local material. In many countries, there is no regulation related to levee safety. Levee management is often fragmented, not at the scale of the actual system which provides protection, and many orphan levees exist. Because after many decades or even centuries without major flood events, it's sometimes difficult to remember their usefulness and sometimes even their existence. This is a fact that has been proven in many occurrences in the past years and decades. Levee systems are often not resilient to overtopping or overflowing, which means we don't have most of the time the equivalent of the spillway that we have on dams. So as soon as they overflow, well, there's a breach and a catastrophic event. And they are usually built upon alluvial foundation without important treatment. So levees are similar to dams. They use the same disciplines, geotechnics, hydrology, hydraulics, civil engineering, etc. Same ingredients, but a different recipe. The levees in flood protection compared to dams, which store water, a given limited volume of water during a flood episode, and limit the water discharge downstream to a given value until the storage capacity is exceeded. They have an effect, this flood storage dam have an effect on flood protection in downstream valley on a more or less long distance according to their storage capacity. But all other dams, reservoirs, as long as there are no opening of gates, they are also reduced to maximum peak discharge during a flood event. On the other hand, levee systems have a different hydraulic action. They actually prevent water to flood a protected area up to a given level, which is called the protection level, as you can see on the picture during the 2003 flood event in the Rhône River in the town of Fourques. But when the water is above the protection level, if the levee system is resilient to overtopping, the inundation is also reduced in terms of duration and or volume. And levees, or said it's not only on rivers but also coastal. So dam and levees at a catchment scale or locally can work together. They can have complementary roles. One to reduce the flood discharge, and the other to prevent water to go in inhabited areas. Some data based on the ICOLD bulletin, which obviously is incomplete because we don't have data in all the countries in the world. Anyway, we find that there are more than 500,000 kilometers of levees in the world. We found at least 20 countries with over 1,000 kilometers. They provide flood reduction to over 700 million people and protect several trillions of dollars in property and economic value. And they prevent annually around billions of dollars in economic damages. Levees protect against flooding up to a given water level, but in the case of a breach, the consequence of the flooding can be a lot worse than if the levee did not exist. Breaches can happen sometimes even before the apparent protection level is breached. For instance, if there is internal erosion, which is sometimes frequent. And as you can see on the table that I want to detail, many recent catastrophic events in the world have reminded, at least in the countries who suffered these events, the importance of safe and efficient levy system. So you see there were a lot of information about countries in Europe, USA, Japan, not in all countries in the world. Levy failures in France. We have a history, modern history that starts in 1993 and 1994 in the Camargue. We have different flood events that are listed in the slide. I won't read everyone, just about the picture, which is a downstream Rhone River again, 10 years after the first ones. And as you can see on the photo, you can see the bridge itself and the flooded area, but on the satellite photo, you can see all that was flooded, everything that was just in blue with red arrows figuring the bridges. So the lessons learned from all these catastrophic events in France, but in most of the countries that suffered flood events involving levee failures, that levees are all heterogeneous, poorly known, there is a problem of management, there is a need for guidance on management and for engineering too. Many disciplines are involved, like for dams. And in France, we have about 9,000 kilometers of levees, about 8,000 inland and 1,000 along the coasts and estuaries. These figures include multi-purpose structures because the flood protection systems, the levee systems, can include levees, but also other structures like roads, railways, groins, breakwaters, river wheels, flood walls, etc., etc. To avoid these failures, there is a need for a proper long-term management and also for professional engineering, which was not the case when many of the levees were built. So the situation in the many countries is the same as was described for France when we started to have the first failures. And also a lesson learned, because we looked also at the past, from the past centuries, that there were levee failures in the past, and levees were repaired, often they were raised. That's not enough, because decades can pass without another major flood event. Levees are forgotten. If they are not managed in the long term, constantly, they will probably also breach during the following next event. So the key issue is to have a long-term management. And also one of the major issues, to be sure there was no problem when water goes over the levee, when the flood protection level is exceeded, you don't need to move from one protected, safe situation to a very, very catastrophic, dangerous situation because of the breach. So levee systems must be resilient to or erosion by overtopping, and includes adding something which acts like spillways for dams. I can refer you to the paper which is listed on the screen to present all that can be done at the scale of an existing portfolio of old structures based on lessons learned in different countries. And also to avoid that, to share information, to share best practice, an international community has started to collaborate on levee issues. And ICOLD is the host of a large part of this international community. It started with the European Club of ICOLD in 2015. During the Stavanger annual meeting, the working group on levees was created. We have now 17 member countries in this European working group. We published a report in 2018. We manage a website, we produce newsletter, we organize some webinars also. Now we will probably organize these webinars under the umbrella of EURcold like today. And in parallel, a few years later, ICOLD itself hosted levies with the creation in 2017 during the Prague ICOLD meeting of the Technical Committee of Levies. The terms of reference were submitted the next year because we were not really ready in 2017. Since then, we have an ICOLD Technical Committee on Levies, which are now recognized as an important topic for ICOLD, as stated in the newsletter of ICOLD number 20. We have a bulletin about the situation on levies around the world that's been approved in 2022. And we have a bulletin that we will submit for approval in 2026, comparing dams and levees on all characteristics in order to facilitate the discussion between specialists of the different types of structures. And finally, as we will have finished what has been defined in our first terms of reference, we will present new terms of reference. So during the next years, ICOLD meetings. So in conclusion, levees can help to protect against flooding, but they need to be given the same level of attention as dams in terms of proper engineering and maintenance to be safe, efficient, and not to increase the risk. And ICOLD and its European club has an important role to play. As you can see, this is an example of a spillway on the Lez River in the south of France to avoid overtopping and failure of levees on the rest of the system. And you have on the next few slides that I will not detail, some example of documents that you can download and read if you want to learn more about levees. And I thank you for your attention and invite you to download this presentation once it will be made available. And thank you again. Thank you for the organizers. Thank you for the audience.
Thank you, Remy. Thank you, everyone. Thank you for your presentations. They were very constructive, and they achieve, and we succeed in the objectives of this webinar. We are now running a bit late. We will try to give replies to some of the questions that you have posed in the Q&A. Let me just a minute to share my screen. Okay. So we have some questions in the Q&A. Just give me 1 second so that I can access the Q&A session. Okay, I will have to stop sharing my screen for that. Excuse me for that. Okay. First of all, there are some questions about sharing the presentations, so we will ask the presenters if they agree that we upload the presentations in the website of EURcold, and we will upload them. And the recording of this webinar will be available a few days later in the Young Professionals Forum YouTube channel. So we will start. We have some questions. Unfortunately, I don't know if we have time for more than these questions. I'm sure that all of us have many things to comment and ask, but we will focus on the questions that have been posed in the Q&A function. Okay, I will start reading the questions one by one, from the oldest to the last one. Emmanuel Guaranta asked, are there economic estimates of avoided flood damages by dams? In the European Union, in 2022, flood damages were 44 billion euros. It would be interesting to know the avoided damages by dams, to really understand their contribution and contextualize. This could be a great input also for policy discussions. I totally agree. I'm not aware any kind of research of this kind. I know that more than 15 years ago, in 2010, in the European Club, there was a research on the attenuation of floods on the attenuation of floods, but I'm not sure if there was any kind of economical aspects in this report. It's very interesting suggestion. I would say that would be a very good idea for a European working group or a research program. So this is a very good proposal that we can keep. I think it's something that it would be it would contribute in public awareness and in providing data which is very useful to the policymakers. This is something that it's of high interest in our community. I don't know if anyone else has any comment on that, or if you are aware of something similar. Anyone from the speakers? Anyone else? No. I would also like to kindly ask all speakers to open your cameras so that we can discuss, and also you will be ready to give your responses. Okay, the next one is to Mateja Klun. From Pashut Alexandre. Did the events of 2023 in Slovenia require to update project and/or safety check floods at dams? If this was the case, did those estimates generally increased with respect to previous ones?
Yes, thank you for the question. Specifically for dams, no specific checks are done, but in the general hydrological sense, there has been methodology published in 2023, so that we have a unified methodology on how to assess hydrological properties based on extreme rainfall events. And it's still an ongoing process. At some point, we will also come to the fact that something specifically regarding to dams has to change, but not at this moment.
Okay, is there any provision in your dam safety regulations in how many years this should happen? This should be done every how many years?
Well, we have a regarding the legislation regarding dams. This is a weak spot in Slovenia. So again, they're treated similarly as any other structures. So we have work to do here. So so far, I can say no.
Thank you. The next question, okay, it's for Mateja as well, from Angelos Rabias. Congratulations for an excellent presentation as always. My question is, how long back do the data you have go approximately? Thank you.
Okay. Well, now it depends what kind of data are we interested in. If we are looking at the historical floods, we have data for water levels for the major floods until 1550. But for example, for Sava River, for the last 50 years, we have time series of measurements. Some of the oldest are 100 years in the history, but generally after the 1947, when the Meteorological Institute was established, then the era of having measurements in Slovenia started. So let's say for the last 50 years for sure, but other extreme events also in the past.
Thank you, Mateja. Then there is a question from Jeremy Savatier. This is a question to Krzysztof. Is there a full feedback report available on this dam failure? Thank you.
Hello, not yet. Not yet. It was not far away, not long time ago, so we don't have this report yet. There are also some investigation of reason of the collapse, some responsible people, unfortunately, must be found. So it has to pass the time to have this report.
Thank you. It would be very interesting when you have the report so that we can
We will share
circulate
it. No
it.
problem.
Yes.
When we'll be ready.
Thank you. The next question is for Teodoro. Given the evidence of changing precipitation patterns and flood regimes due to climate change, do you believe traditional stationary statistical methods are still appropriate for flood hazards and risk analysis? Should the EU be moving towards mandating non-stationary approaches in flood risk assessments, similar to what's already been implemented in countries like Australia and the US?
This is a good question. And the stationary or non-stationary regimes. We have the flood of 2024 has shown us that the rainfall has been very extraordinary. And very extraordinary. Never have produced rainfalls of 700 millimeters in that area of Spain. We have had extraordinary rainfalls in some coastal areas, in the area of Denia, of Javea, but not in this area. We are studying all the registers. We are working on it. The studies carried out by Center for Geographic Studies of CEDES told us that the maximum rainfall are changing according to the climate change data. But surely we will have to work with non-stationary regimes in the future. Now we are really very concerned with this problem. No.
Thank you, Teodoro. I'm sure it will concern many countries. The next one is from Evangelos Rapias to Ioannis Karavokyris. A question for Ioannis Karavokyris, if I may. Congratulations for a very interesting presentation. I'm curious how a spillway equipped with fuse gates would perform in the examples you showed. Fuse gates combine both free, uncontrolled, and gated spillway benefits, often enabling to have both short spillways without raising the dam crest, with no O&M costs or human interventions to operate. Passive system. You may already have considered this.
Thank you, Angelo. Yeah, it's fuse gate spillways are very interesting always for us in a number of applications. The specific issue that we have to face with dams, particularly multipurpose dams with an important flood routing component, is that we want high freeboard. So high head, and there may be some challenges with designing high head fuse gates that don't let's say float away until really high events. But this is, I think, a topic on its own, and I'm sure you have also a lot of knowledge on this one. It is very interesting to discuss it, but I think you understand the problem that we have. On the one hand, we don't want to lose the fuse gates, but on very rare events, on the other hand, we want to create quite high heads, even on more frequent events, like 1 in 50 or 1 in 100. I would be very interested to discuss it. Thank you.
Thank you, Ioannis. And in Thessaly, we have to promote the dams that have already been assessed. The next question is for Murano, for Rinaldo. Following up on your point about Italy's aging dams designed with imperial methods, actually a situation similar across much of Europe. Given both the aging dam infrastructure across Europe and commitments under the Water Framework Directive and biodiversity strategy, how should member states strategically balance flood risk management needs with river restoration goals when making decisions about dam rehabilitation, modernization, increasing the reservoir capacity, or decommissioning, removal?
A very interesting and complex question.
From Miguel Silva.
Okay. I think it's not easy to give an answer to this question. It is very complex, actually. It's clear that the different needs of the territory are often in contrast each other, and it is not easy to face all of them together. In any case, I believe that a territorial management strategy is necessary. A strategy that is very attentive, is very oriented to the various needs. And of course, some of these needs conflict each other. I think it's necessary to develop thoughtful cost-benefit analysis of the various solutions, identifying and maybe identifying any priorities that are more focused on protecting the populations. But I think that there is a great work to do in that direction. It's not easy to have one answer to this question. It's very complex, but very interesting.
Yes, the balance between the Water Frame Directive and the Flood Directive is really challenging. The next one is to Teodoro. Given the complexity of flood management, which involves multiple approaches implemented by various administrations, institutions, and even individual self-protection, cooperation and coordination appear to be crucial, as highlighted in several presentations. In this context, which organization or administration should take the lead? Should it be at the national level, or should European institutions take the primary role? This is a question from Alfredo Granados.
I completely agree with Alfredo that the coordination, cooperation, collaboration between administration is absolutely necessary. Absolutely. But it's true that we have a regulatory framework in Spain that establishes competencies in order to manage floods. And we have to take into account this framework. We can change the framework. If not, it's not possibilities to establish regulatory changes at a national scale. But at this moment, all the administration must cooperate, take into account the respective competencies. The state, in the case of the basins that are managed by the state, must give information about the flow ditches in the main rivers, the management of the reservoirs, etc. But then the regional governments are in charge of the civil protection coordination, no? And it's very important, the coordination of regional institutions and state. That is clear.
Thank you, Teodoro. I have a last question from the Q&As to all. I'm curious about the scientific development in your countries in the field of hydrotechnical engineering. Do you have problems with too few engineers in the area? How much do your governments invest in the development of design stuff? Perhaps this is a conversation for another meeting. Okay. The truth is that I think that this is a pan-European problem. Engineers, and this is what we are trying to do. We understand that there is shortage and lack of interest, and this is why we are trying to promote our industry. We need a lot of engineers in the ministries, in the consultancies, in all fields of dam engineering, and especially now that we know that in the future, with all this aging infrastructure, in order to maintain it effective and being able to attenuate the floods that we want and provide all the benefits that they provide, we need people to maintain it. And this is what we are trying to do. We're also trying to do that a lot in EURcold and in ICOLD. Okay, it's a very big discussion, a very big discussion. I don't know if any of the speakers have something to add in this question.
As you said it, it's a big discussion.
It's a big discussion. Okay, I'm sure that many of us have many more questions, but we are 35 minutes late. So I think that we have to move to a conclusion and thank everyone for your contribution. I really believe that the webinar was very constructive. We will share all the information that we have from the webinar and is available. We have confirmed that dams working together with other, of course, flood control measures can play a vital role in Europe. Continuous adaptation and compliance with national regulations and European directives are essential to meeting future challenges, particularly as our infrastructure continue to age, as we have seen. There are assessment and emergency action tools available, but they have to be further developed. Combined with proper maintenance and operation, this ensures that dams can effectively mitigate floods and their downstream impacts. And it is vital to communicate the insights that we have discussed today broadly to policymakers, stakeholders, and the public to ensure that the importance of our work is clearly understood. Thank you, everyone. Thank our speakers for your contributions, insightful contributions. Thank you, everyone, for staying with us for so many hours. And we are looking forward to seeing you and welcoming you again in our future webinars, probably the next one in Levies. Thank you so much.
Thank you.
Thank you.
Bye.
Thank you.
Thank you.
Thank you all. Thank
Bye.
you.
Bye-bye.
Thank you. Bye.
Bye.